There's a specific kind of arrogance that I think comes with living in the modern world.
Hmm.
We look back at history,
Yeah.
right, at people who thought the Earth was flat or that the sun revolved around us, and we sort of smirk.
Oh, absolutely. It's the ultimate hindsight bias.
How could they be so blind?
It's just so easy to see the truth when you have a high-resolution textbook open in front of you. But if you strip that away,
Right.
if you're just a person standing in a field in, say, 300 BC, it is a totally different story.
Exactly. And that is why today's deep dive is, I think, going to challenge that smirk. We're unpacking Chapter 15, The Nature of the Solar System.
Yeah.
And the mission isn't just to memorize the order of the planets. It is to track one of the most difficult, grinding, intellectual shifts in human history.
We're tracking the move from the geocentric view,
Earth in the center.
Earth in the center, yes, to the heliocentric view. And what's fascinating, and what I think we often forget, is that for thousands of years, the wrong answer was actually the most logical, scientific answer they had.
That is the hook for me. The ancients weren't stupid. They were just working with the data available to them. So let's set the stage. We're going back before the telescope,
Way before.
before NASA. What was the baseline assumption for humanity?
The baseline was, well, I'm standing still.
Yeah.
And honestly, if you go outside right now, it still feels true.
It does.
You don't feel the Earth spinning at 1,000 miles an hour. You don't feel us hurtling around the sun. You feel solid ground. And when you look up, you see the sky moving around you.
It's the ultimate optical illusion. So we have these ancient cultures, the Chinese, Babylonians, Egyptians. They're looking up and they're seeing patterns. The source material mentions they were obsessive record keepers.
Oh, they had to be. This wasn't just a hobby. It was about survival, agriculture, calendars, religious festivals. Everything depended on the sky. If you didn't know when the sun would reach a certain point, you wouldn't know when the floods were coming. The Chinese, for instance, have records of guest stars.
I love that term, guest stars. It sounds so polite.
It's poetic, isn't it? But it describes exactly what they saw. A star that, visits for a while and then leaves. They recorded one in 1054 CE that was so bright it was visible during the day.
Wow.
We know now that was the explosion that created the Crab Nebula. They also tracked Halley's Comet for 1,000 years without knowing what it was.
And they thought it was a bad omen, right? Like, there's a smear in the sky, the emperor's definitely going to die.
Usually, yeah, comets were agents of chaos. But the point is, they totally nailed the what. They knew exactly where Jupiter would be in the sky next Tuesday. They had the data.
But they completely misunderstood the why.
Exactly. And that misunderstanding gets solidified by the Greeks. This is where we get the concept of the crystal spheres.
Aristotle and Ptolemy.
Enter Aristotle and later Ptolemy. This is the geocentric model that dominated Western thought for over a millennium. Earth is a sphere, it's motionless, and it's in the absolute center of the universe.
And everything else, moon, sun, planets, orbits us in these perfect crystalline circles.
Perfect circles.
And again, to be fair to them, they had some incredibly strong arguments for this. It wasn't just, we feel still.
No. They argued that if the Earth was spinning, birds would get left behind. If you threw a rock straight up, it should land miles away because the Earth moved underneath it.
Which makes sense.
It's sound logic if you don't understand inertia. But the third argument was the simplest. Everything looks like it circles us.
Until you look closely at the planets, specifically Mars. This is the glitch in the matrix.
Retrograde motion. This is the headache. Most of the time, Mars moves east across the background of stars night after night. Simple. But every couple of years, it stops, it drifts backward westward for a few weeks, and then it turns around and goes forward again.
It does a little loop-de-loop in the sky.
Precisely. Now, if Earth is the center and everything moves in simple, perfect circles around us, that makes zero sense. Why would a planet just stop, throw it in reverse, and then drive forward again?
So how did Ptolemy explain it? Because his model survived for 1,300 years. He must have had a fix that was really convincing.
He did. It was a masterpiece of mathematical gymnastics called epicycles.
Epicycle.
Basically, he said planets don't just orbit Earth in a big circle. They orbit Earth while also spinning in a smaller circle of their own.
Okay, I'm trying to picture this. It's like the teacup ride at an amusement park.
That is the perfect analogy. You are spinning in the teacup, that's the epicycle. But the whole platform, the friend, is also rotating. From the outside, your path looks like a curly Q.
So you're going forward, then you loop back, then you go forward again.
Exactly.
That feels incredibly over-engineered. It's like adding duct tape to a broken engine.
It was. By the end, they had epicycles on top of epicycles just to make the math match the observations. But And this is key, it worked. It predicted the planetary positions accurately enough that nobody questioned it for over a millennium. It was a usable fiction.
Until we get to the modern explanation, which is so much simpler. The source uses the highway analogy, and once you hear this, you can never unsee it.
It really cuts through all the noise. Imagine you are driving a fast sports car on the highway. That's Earth. We are in the inside lane closest to the sun, and you are coming up behind a slow-moving truck. That's Mars in the outside lane.
Right, so I'm gaining on the truck.
As you pull up alongside it, it looks like it's moving forward, but the second you pass it, because you're going so much faster, the truck appears to drift backward against the distant landscape.
Even though the truck is still moving forward at 60 miles an hour, it's an optical illusion.
Caused by our relative speed. Precisely. We orbit the sun faster than Mars, so when we lap it, it looks like it's going backward relative to the stars. No epicycles needed.
But that realization required a massive leap of faith. It required someone to say, maybe the Earth isn't the motionless center. And that brings us to the Avengers of astronomy.
The Big Five.
First up, Nicholas Copernicus.
The Quiet Revolutionary. A Polish astronomer, early 1500s. He looks at Ptolemy's messy system of wheels within wheels and basically says, this is too ugly to be true. Nature should be simple.
So he puts the sun in the center.
Puts the sun in the center. But this was heresy. I mean, not just scientifically, but religiously.
Dangerous heresy.
Oh, yeah. It contradicted the church, the Bible, common sense. That is why he waited until he was literally on his deathbed in 1543 to publish his famous work, De Revolutionibus.
But here's the thing I found really interesting. Copernicus wasn't actually totally right, was he? He made the big shifts, sun-centered, but he held on to one bad habit from the Greeks.
He just could not let go of the perfect circle. He assumed planetary orbits had to be perfectly round because, philosophically, circles were divine and unbroken.
Which meant his math didn't actually work much better than Ptolemy's.
It didn't. That's the tragedy of it. Because he insisted on circles, his model still drifted off course. He actually had to keep using some small epicycles just to make it work.
So scientifically, it wasn't a slam dunk yet.
Not at all. It was just a cleaner, albeit heretical, idea.
To get the slam dunk, we needed better data. Enter the wildest character in this story, Tycho Brahe.
Tycho is fantastic. A Danish nobleman, incredibly wealthy, and famously eccentric. He lost part of his nose in a duel over a math formula.
We're kidding.
Nope. And he wore a metal prosthetic for the rest of his life.
That is dedication to mathematics.
Yeah.
But his contribution was his observatory, Uraniborg.
Right, and we have to remember, no telescope yet. It hadn't been invented. Tycho built these giant protractors, and for 20 years, night after night, he mapped the stars and planets with unprecedented precision.
He was the ultimate data collector.
The ultimate. But the irony is, he was doing all of this to prove Copernicus wrong.
He was a geocentrist.
A staunch geocentrist. He didn't believe the Earth moved. And he had a very smart scientific reason for it, which he called stellar parallax.
Okay, this is a concept that can be tricky, but the source suggests the finger experiment. Let's do it.
Okay, listeners, try this right now. Hold your finger up at arm's length. Now close one eye. Now switch and close the other.
My finger is jumping side to side.
It jumps relative to the background wall, right? That is parallax, the apparent shift of an object because you're viewing it from two different angles.
Okay.
Tycho reasoned. If Earth is moving around the sun, then in January we're here, and in July we're way over there on the other side of our orbit.
That creates a huge baseline, a massive viewing angle change.
Exactly. So we should see the nearby stars jump back and forth against the distant stars, just like your finger jumps against the wall.
So Tycho looked for that shift.
He looked for it for years, strained his eyes trying to find it, and he saw zero shift.
So he concluded the Earth isn't moving.
Which, again, is a logical conclusion. If you predict an effect and you don't see it, your theory is usually wrong. But Tycho failed to realize just how staggeringly, mind-bogglingly far away the stars are.
The shift was there.
It was there, but it was microscopic, far too small for the human eye to see. You need a powerful telescope to measure it.
So he was limited by his technology.
Right. But his legacy wasn't his theory. It was his data. He left reams of precise numbers on the position of Mars.
And that data fell into the hands of his assistant, the man who would change everything, Johannes Kepler.
And Kepler is the turning point. He takes Tycho's Mars data, which he knew was the best in the world, and he tries to force it into Copernicus's circular orbits. He spent years battling this problem.
And it doesn't fit.
It almost fits. There's a tiny discrepancy, an error of 8 arc minutes. Most people would have just written it off as an observation error.
Oh, Tycho must have sneezed.
Exactly. He had a bad night. But Kepler knew Tycho was too good for that. He trusted the data more than the dogma.
And that trust leads to the first law of planetary motion, the moment the crystal spheres just shatter.
He realized the orbit wasn't a circle, it was an ellipse, an oval.
That seems like such a small detail to us now, but at the time, that was revolutionary.
It was everything. It fixed the math perfectly. No more epicycles, no more wheels within wheels, just elegant, elongated paths. And he didn't stop there. He found a second law. Planets change speed.
They aren't on cruise control.
No. When they get close to the sun at perihelion, they speed up. When they're far away aphelion, they slow down, like a slingshot effect.
And his third law tied distance to time, showing the whole system was a unified machine.
P squared equals A cubed. Exactly. So Kepler gives us the how. He describes the motion perfectly, but we still need the smoking gun. We need to see that the Earth isn't the center.
Enter Galileo Galilei, and the piece of tech that changed the world, the telescope.
Now, Galileo didn't invent it.
Right, Dutch lens makers.
But he improved it. He got it up to 30x magnification. And crucially, he didn't use it to spot ships at sea. He pointed it up.
And what he saw in 1609 just destroyed the geocentric model overnight.
The list of evidence here is absolutely devastating for the old view.
Let's run through it. First up, Jupiter.
He looks at Jupiter and sees 4 little stars caught in its gravity orbiting it. Night after night, they dance around the planet.
Which proves that not everything revolves around Earth. There could be other centers of motion.
Exactly. Then he looks at the moon. The ancients said heavenly bodies were perfect, smooth spheres. Galileo sees mountains, craters, shadows. It's a rock. It's a world just like Earth.
He looks at the sun, sees sunspots.
Blemishes. That moved. The sun itself was rotating, but the big one, the absolute nail in the coffin, was Venus.
The phases of Venus.
This is the hardest one to visualize, but the most important geometrically. In the Ptolemaic, Earth-centered model, Venus is always located between Earth and the sun.
So if the light is coming from behind it, we should only ever see it as a crescent, like a sliver.
Right. You should never, ever see a full face of Venus. But Galileo watched Venus for months. He saw it go from a crescent to half to gibbous to full.
And the only way you can see a full Venus lit up like a full moon is if it's on the opposite side of the sun from us.
Which means it's orbiting the sun, not us. It was irrefutable proof.
Of course, irrefutable doesn't mean accepted. The church wasn't exactly throwing him a parade for this.
No. Galileo ended up under house arrest for the rest of his life. But the cat was out of the bag. The geocentric model was dead. The telescope had killed it.
Okay, so we have the correct model now, heliocentrism, but we still have a missing piece. Kepler described the ellipses. Galileo showed us the physical reality.
Yeah.
But why? What keeps a planet moving in an ellipse? Why doesn't it just fly off into space?
That answer requires the final giant, Sir Isaac Newton.
A great synthesizer.
Newton takes 2 concepts and just welds them together to explain the entire universe. First, inertia. This was actually Galileo's idea first.
An object in motion stays in motion.
Stays in motion in a straight line unless a force acts on it. So if you throw a baseball in deep space, it doesn't slow down. It just goes straight forever.
Okay.
But then Newton introduces universal gravitation. He realized that the sun is massive and it is pulling that baseball or that planet toward it.
So an orbit is just a fight between those two things.
It's a perfect compromise. The planet wants to fly straight past the sun because of inertia. The sun wants to suck the planet in because of gravity. The result is a curve.
It's falling.
The planet is constantly falling toward the sun, but it has so much forward momentum that it keeps missing.
Falling but missing. I love that description. That is what keeps the Earth afloat.
That balance creates the elliptical path Kepler found. Newton provided the physics that made Kepler's math inevitable.
Okay, so we've figured out the mechanics of the solar system. Let's zoom out to the very beginning. Where did the system come from? The source covers the nebular theory.
This is our origin story. They go back 4.6 billion years. We start with a massive cloud of interstellar gas and dust floating in space. A nebula.
Mostly hydrogen and helium.
Mostly, yeah. And then something disturbs it, maybe a nearby supernova shockwave, whatever it was. Gravity kicks in, and the cloud starts to collapse inward. As it shrinks, it begins to spin.
Like a figure skater pulling their arms in to spin faster.
Exactly that. Conservation of angular momentum. It spins faster and faster, and it flattens out into a disk. The material in the center gets incredibly hot and dense. That becomes the protosun.
And the rest of the disk becomes the planets.
Well, yeah, the dust and gas start clumping together. These little clumps grow into asteroid-sized chunks called planetesimals.
Literally pieces of planets.
Yes, they collide, they stick, and they grow larger and larger.
But here's the part that explains our neighborhood's layout. Why are the inner planets, Mercury, Venus, Earth, Mars, small rocks, while the outer planets are these massive gas giants? It's not random.
No, it's all about temperature. We call it the frost line. Near the new sun, it was incredibly hot.
Too hot for ice.
Way too hot. Ice is like water, methane, ammonia, they all vaporized. So the only things that could remain solid to clump together were metals and rocks.
So the inner planets are just made of the leftovers, the stuff that didn't melt.
Exactly. That gives us the terrestrial planets. But past the frost line out, where Mars ends and Jupiter begins, it was cold enough for ice to form. And since there is way, way more ice and gas in the universe than rock, those planets grew massive.
They just had more construction material to work with.
Much more. They got so big that their gravity became intense enough to actually capture the light gases, the hydrogen and helium that were floating around the nebula.
So they became vacuum cleaners for all the gas.
And swelled into the Jovian giants we see today.
It's amazing how elegant it is. The temperature 4.6 billion years ago dictated the entire map we live on today.
It really ties the whole story together. From the ancients watching the sky, to Newton's math, to the thermodynamics of gas clouds, it is one consistent physical story.
So if we step back, what is the big takeaway here? Aside from all the physics and the history lessons.
For me, it's about the courage to question intuition. For thousands of years, the smartest people on Earth believed something false because it felt true.
Earth feels stationary. It looks like the center.
And they built incredibly complex systems, those epicycles, just to defend that feeling. They were doing mental gymnastics to avoid facing the data.
Right. They were force-fitting the universe to match their assumptions.
And it took people like Copernicus, Kepler, and Galileo to look at the data, the weird little wobble of Mars, the phases of Venus, and say, maybe the universe doesn't care about our assumptions.
It's a humbling thought. Science isn't about confirming what we believe. It's about following the evidence, even when it leads somewhere uncomfortable.
Absolutely. The data is the only authority.
So here is a thought to leave you with today. The ancients were 100% convinced they were the center of the universe. It was just common sense. Today, we look back and we smile at that error. But it makes you wonder, what scientific truths do we hold today simply because it feels intuitively right? What is the geocentric model of our time that the next Galileo is going to overturn?
That's the question that keeps science exciting. We are never finished learning.
Keep looking up. We'll see you on the next Deep Dive.